Okay, so we talked about ratios and proportions. We're talking about direct proportions, direct ratios, and inverse ratios and how they work differently. Our direct proportions or direct ratios any sort of direct relationship means when one value gets larger, the other value has to also get larger in some sort of a proportional manner. Or the opposite's true. If one value gets smaller, the other one has to get smaller. One of the greatest examples, or the most common examples of this was similar figures. We have a triangle that gets enlarged. Let's say we have sides of 6, 9, and 15. Actually, that ain't going to work. Let's try 6, 9, and 14. And over here we'll have 15, x, and y. If one side, or if one triangle is just an enlargement of the other, then all of those sides had to be increased by the same factor, multiplied by the same enlargement factor. Now this one, because they're in the same orientation, we can match up which sides go with each other. They're called corresponding sides really easily. But if one of them's rotated or flipped over or whatever, a lot of times you need to know the angles, which angles match up. It's like this angle and this angle are the same, and this angle and this angle match up as well. And once you know which angles correspond or which angles are equal, then you know which sides match up. For example, we know the 6 has to go with the 15 because they're both bordering this same angle, and then this larger obtuse angle here that isn't marked. So they're between the same two angles, they must be corresponding sides. And since we know the lengths of both of them, that gives us our enlargement or reduction factor, depending on how you want to look at it, for the two triangles. The 6 becomes the 15. We have one relationship. Now, if you recall, these proportions have relationships in both directions. The 6 and the 15 were related because they were corresponding sides. They were the same side of the two different figures. Now going this way, there also has to be a relationship. Whatever number we put here has to have some sort of relationship with the 6. Whatever number we put here has to have some sort of a relationship with the 15. Now to figure out what numbers we're going to put there, usually we decide which side we're going to try to find first, x or y. And which one do you guys want to find?
Y.
Y? Okay, so where's the y going to go? Top or bottom? It's going to go on bottom because its relationship with the 15 is that they're from the same figure, from the same triangle. So it has a relationship with the 15. It does not have any relationship at all with the 6, so it couldn't go on top. Now, of course, whatever goes here not only has to be related to the 6, it also has to be related to the y. Well, the y corresponds with the 14. So that's its relationship with the y, is that it's the corresponding side from the other figure. 14 is related to the 6 because they're from the same figure. We also talked a little bit last week about you could set up this proportion in different ways. When we solve this, we're going to do 15 times 14 is 210, divided by 6 is going to give us 35. But anyway, we said you could set this up in different ways. Those relationships have to hold true, but they don't have to stay in the same direction. Instead of putting 6 over 15, we could have done this. We could have said 6 is related to 15 in this way. We put the relationship there horizontally instead of vertically. What goes down here, the other number that's going to be related to the 6 will be the 14, and the y is still related to the 15. So even though that proportion looks way different, when you go to solve it, it's still 14 times 15 divided by 6, just like it was over here. So don't think that just because I set up my proportion like this, that yours can't look different and still be the same relationship and be a correct proportion. Well, today we're going to look at applications of those similar figures and where they come into reading blueprints and stuff like that. One of the applications we're going to talk about is a taper. A taper usually describes something that is round, circular, but does not have a constant diameter. We talked last semester about cylinders. do that a little different. And a cylinder is something that is round, but it has a constant diameter throughout. Then we also talked about cones, which are round, but their diameter slowly decreases down to nothing until it comes to a point. Well, a taper is kind of somewhere in between there. In fact, you can think of a taper almost as a cone with the tip of it cut off. Geometrically, actually, the term for it is called the frustum of a cone. But anyway, in machining, a taper is that round feature that goes from having a larger diameter to a smaller diameter over a given length. So the larger diameter we're going to call capital D. Big D for the big diameter. Smaller diameter we're going to call little d. If we're using standard measurement, in other words, inches and feet, the small and large diameter are usually given in inches. The length, which we're going to call capital L, is also often given in inches, but it's going to be converted into feet. The reason for that is that the proper term, a taper, is almost always given in terms of taper per foot. And we saw this formula a little bit at the end of last semester, where to calculate the taper, it is the large diameter minus the little diameter over the length, where the length is divided by 12 to convert that length into feet. So let's say we have a metal spindle for a table leg, or whatever, metal leg for a table. Let's say it goes from being 2 3/4 inches down to being 1 3/8 inches over a course 28 inches. Find the taper per foot. Well, our taper per foot, what's going to go on top for big D? 2 3/4 minus 1 3/8 over 28 divided by 12. Now when we do this, remember this line across here, that fraction bar, recall our order of operations, that's telling us we have to do everything on top first, then we have to do everything on bottom, then we can divide. So 2 3/4 minus 1 3/8. 1 3/8, very good. 28 divided by 12? 2.33 or 2 1/3, right? When you're doing these, you need to do one of two things. You either need to use the fraction form, because fractions are more exact than decimals, or you need to keep it in your calculator. And I'll show you that in just a second, how you keep that in your calculator. I say fractions are more exact than decimals because this would have been, in decimals would have been 2.33333. No matter how many of those threes you write, you're eventually going to round it off. As a fraction, it stays exact. So now we're going to divide. Now when we divide fractions, of course, we usually write them horizontally like this. What do we have to do to divide fractions? Convert them to improper fractions. They're mixed numbers right now. We got to take them improper. So 1 3/8 will be 11/8. 2 1/3 will be 7/3. And then we're going to multiply by the reciprocal. So 11/8 times 3/7 will give us 33/56. So if we wanted to leave that as an exact fraction, it's a 33/56 of an inch per foot. It becomes a rate. Or you could divide out the 33 divided by 56. Typically we give our tapers in decimals then, once we're done calculating, out to anywhere from 4 to 6 decimal places. So this will go to 4 decimal places here, 0.5893. inches per foot is that taper. So that means is for every foot of length, the diameter decreases by 0.5893. So let's say we have a funnel to feed an injection molding machine. So the pellets are coming in from a bin into this funnel to feed into the machine. And let's say up top here, we have a radius of 6 inches. And down bottom here, we have a radius of 3/4 of an inch. And this is going to happen over the course of 18 inches. You guys tell me how to set up the formula here. What's wrong with that? There you go, Jared's got it. Yeah, right now that is a radius. Those are radii. We need diameters. So it is 12 minus 1.5. Very good. Over 18 divided by 12. So 12 divided by 1.5 is 10.5. 18 divided by 12, Tyler said, is 1.5. So now we're going to divide. 10.5 divided by 1.5. What's 10.5 become? 21 over 2. Good. 1.5. It's 3 over 2. Perfect. 2's cross cancel. 21 and 3 can be divided by 3 to give me 7 and 1. Oops, 7 and 1. So we got 7 over 1 or just 7. So that taper is 7 inches per foot. I see this commonly, a mistake made on this, they'd say it's 3.5 inches per foot, but that's because they forgot to convert the radii into diameters. So be careful with that. Let's look at the other side of this. There's something you're going to come into called Morse tapers. Morse tapers are a standard set of tapers that are out there in the industry. You might have like a number 5 Morse taper, which is 0.296, I can't remember the numbers now, but so many inches per foot of length. So if you're given that you need to follow a set standard taper, you need to be able to figure out dimensions from that. So let's say that you are told you need 0.2585 inches per foot of taper. And you have a part that has a large diameter of 3¼ inches. And this is going to go over a length of 20 inches, and you need to know what the small diameter is going to be. So now in this case, we look at our formula, and we're going to plug in what we know. Well, in this case, we know T is 0.2585. We know that big D is 3 1/4. We do not know little d. That's what we're looking for here. L is 20. And now we're going to have to solve this to try to find little d. Well, just like before, we're going to follow order of operations, which tells us to do everything on top first. Was there anything we can do on top? No, there's not. Nothing we can do over on the left side. Nothing we can do on top. On bottom, is there anything we can do? You bet. 20 divided by 12 is 1 2/3. Good. 1.666. Those are some decimals you should be recognizing by now, by the way. 0.33333 is 1/3, or 0.66666. And there should be others that hopefully will start coming to you. But those I hope you have down by now. So now we need to solve this for little d. There's 3 things that have been done to little d here. This minus here, remember we said that when we see a minus, a subtraction in front of a variable, we treat that as -1 times that variable. So little d has been multiplied by -1. The 3 1/4 is positive, so that's been added to it, and then it was divided by 1 2/3. So to solve this equation, to take it back apart, we reverse that. So what's the first thing we're going to do to take this apart? Multiply by 1 2/3, because that was the last thing that was done in building this equation. So when we go to solve it, that's the first piece that comes off. We multiply by 1 2/3, which takes off that piece that's dividing by 1 2/3. Well, now this is going to take a little bit of work. We've got 0.2585 times 1 2/3. Now I said the other option, instead of keeping it as fractions, is to keep it in the calculator. So I'm going to put in my 1 2/3 first, because my calculator isn't a fraction calculator, so I got to kind of fool it into doing 1 2/3 like that. Times 0.2585. Now, even though that is rounded on the calculator screen of 0.666666667, as long as I keep it in the calculator, it's not going to round it off. My final answer will be a decimal, but it's not going to have all the round off errors that I would have by writing it down and typing it back in at every step. So I multiplied by that, so I got 0.4308. Now I'm going to write down 0.4308 here, but I'm going to keep my calculator from being cleared, because I'm going to come back and use the calculator and just keep adding into it so that I don't lose any of those round offs in the decimal. Now what's the next thing I would have to do here to solve? I'd have to subtract the 3 1/4, right? That would leave me with just the -1d here, subtracting 3 1/4 over here. So now I'm going to take that answer that's in my calculator, I'm going to subtract, and again, I've got to kind of fool my calculator into doing fractions, 3 1/4. Gives me a -2.8192. And now all that's left to do to solve this is divide by -1. So that becomes a positive 2.8192. Is the small diameter. I could do my calculator, divide by the -1 if I want to. Give me the same thing. If I need to go more digits, I do have my calculator display here. I can go up more digits. And what's in the calculator display, of course, this last digit here is rounded, because your calculator always rounds that last digit if it has to. But we know that it's accurate up to that point because I didn't write it down and type it back in. Other things that we use these similar figures and triangles for are sometimes called aspect ratios. Now, aspect ratios come into place in a lot of things. You guys did your blueprint reading last semester. Aspect ratios come in when your scale drawings. You have, a 1/8 to 1 scale. So that means what's on the paper is 1/8 of an inch for every inch in real life. But aspect ratios can also come into place when you have a shape like this. Where you have a sloped surface. And let's say that this here is, we're going to go millimeters, 8 millimeters here, 32 millimeters here. We're going to give this a 3:2, sometimes called the slope or aspect ratio. Let's see here. We go 40 millimeters here. And what I'm asking you to find is I'm going to ask you to find this dimension right here, A. But while we're at it, we'll find B and C here as well. Now looking at this, there's one of those dimensions, A, B, or C, that we can find right away without doing much of anything. Can you tell me which one it is? C, how do you find it? Yeah, it's 32 all the way across here. It's 8 across here. If we subtract 32 minus 8, what's left over has to be C. It has to go the rest of the way across. So what's that going to become? 24 millimeters. Perfect. Now, from that information, we can find dimension B here, because dimension B and C combine to describe this sloped surface. Well, that sloped surface is also described by this 2 to 3 slope. when we're talking about a slope, and we mentioned this earlier, rise over run, or vertical over horizontal. It's the standard way of listing it out. You can put it the other way as long as you flip both numbers, but it's just the standard way of doing vertical over horizontal, rise over run. So the 2 to 3, the 2 is going to go on top because that's the vertical, and the 3 will go on bottom. Now over here, the top number is the vertical. So which one is that going to be, C or B? It's going to be B. Do we know B? No. That's actually going to end up being what we look for here. On bottom then is the horizontal. That would be the C, or 24 millimeters. And now we can find B by cross multiplying and dividing. 2 times 24 divided by 3 gives us 16 for B. So B is 16 millimeters. Now, of course, we can find A relatively simply. We have 8 here. From here to here is 16, which would make 24 total. 40 minus 24 is 16 millimeters. There we go. Any questions? So here we've got an object that's going to have a 2 to 1 slope factor. Now I'm going to label it this way. So it's 2 to 1 on both sides. You know, both sides have the same slope. I want to find A, B, and C. And I need to label this yet, don't I? Why don't you guys tell me where to start? What part of this can we find first relatively easily? A, okay. Oops, come here. How do we find A? Okay, we add these two together, which actually comes out to be 1 inch exactly. You know it's 1.6, so we're going to subtract that from 1.6. So we have A is 0.6 inches. Now what? Okay. So that's 1, 2, or we'll actually put it over here if we want to. We know this is dimension B, right? This is the height. Do we know this dimension? What is it? Where did that come from? Half the 0.6, yeah. 0.6 is all the way across. Since this taper is the same on both sides, this valley down here has to be halfway across. Good. How do we find B? 2 over 1. B over 0.3. Good. B is the vertical and 0.3 is the horizontal. So we cross multiply and divide. B is 0.6. What's next? 1.2 minus 0.6 gives us that C is 0.6. Good. For some reason I must have 0.6 on the brain this morning.
But that's only true if tapers are the same.
That's only true if the tapers are the same, yes. At some point we will get into problems where I do give you something like that, where I might have, this might be a 5 to 2 taper here, and this might be a 1 to 1 taper here. And then we know these dimensions and these dimensions, so we know what it is across here. So then we'll have to use this information then to figure out where that point is, the valley is. But that requires a system of equations, which you guys did last semester, so we better be able to do it. I won't put you through that yet for another few days. But something to look forward to. I'll let you feel good about yourselves for a little while longer. Other ones we'll run into. Outside of the geometry of things that you're going to see, you're going to have cutting speeds. So let's say you have a feed rate, I should say, of let's see. 0.004 inches per revolution. And you want to know how far you can cut in a minute where you have a machine that is running at 600 RPMs, revolutions per minute. This doesn't look like it, but it's a ratio. Remember, we talked about or not ratios, but it's a proportion. We talked about rates also being in proportions. This is a rate because it's not comparing two things that are the same units. It's comparing two things that are different units, inches and revolutions. And when we see a rate, remember, so whenever you see this in your units, you need to think of a fraction. This is 0.004 inches per 1 revolution. This over here, 600 revolutions per 1 minute. Oops. Now, obviously, they don't have the same label, so I'm not going to put the whole things together. But what I can do is this. I can just say I want to know how far I can cut in 1 minute. So this is already per 1 minute, so I can just use that 600 revolutions. So if it's 4 thousandths of an inch in 1 revolution, how many thousandths of an inch in 600 revolutions? And now it's a matter of cross multiply and divide. Now, of course, whenever you see a 1 here, we know the dividing doesn't have to happen. 0.04 times 6 is, what's that? 2.4, good. So in 1 minute, that can advance 2.4 inches. You might also have a cutting speed where you can go, you might figure out that you can go 3.8 inches per minute. And you want to know how long it is going to take to make a cut that is 28 inches long. Same type of formula, same type of setup is going to be here. 3.8 inches per minute becomes 3.8 inches in 1 minute. Where's the 28 going to go? On top, because it's inches. We have inches here, we got to have inches here. And now it's going to be cross multiply and divide. So 1 times 28 is 28, divided by 3.8 gives us 7.37 minutes. Any questions? Okay. We're going to have, actually, we're going to be working out of 2 different packets today. One packet I know you already have. That's the one that has the measurements on the front of it. Where we added and subtracted the measurements and stuff like that. If you look in that packet, let me grab my copy of it quick so I make sure I've got the right page numbers for you. Looking in that packet, you guys should be able to do numbers 1 through 39 with what we've discussed today. So numbers 1 through 39, or not 1 through 39. We already did 1 through 30, so 31 through 39. And then also 42 and 43. If you really want to look ahead to a challenge, number 45 on the next page is one of those I was talking about where the 2 slopes are different. We're going to have to come up with a system of equations. So that's one you guys can play with if you really want to. Also, I've got another packet I'm going to give you. At least I think you need a new packet. It's not in your old one. Actually, it must be in your old packet. In the other packet you guys have, page 234. Sure that's in here. Yes, it is. So in the other packet, page 234, let's just have you do 1 through 7 right now, talking about tapers. So it actually spills over onto page 235 and 236 as well. That'll be enough to keep you busy for tonight. 234.
Lies, John.
Anybody want to get their test?